All right, hello. My name is ClareSaiki, and I'm a PhD. Actually, restart. Okay. Hello, my name is ClareSaiki, and I'm a PhD candidate at UC Santa Barbara. I'm specializing in remote sensing, and my research focuses on remote sensing of wildfire fuels and how fuels relate to the emissions that result from fire. For some background, there are a lot of benefits for using remote sensing and geospatial data to research fire. Remote sensing can help contribute a lot of understanding to the fire community because it provides a timely and large-scale perspective on fire that we cannot gain from anywhere else. This information is quickly translated into actionable information used in modern-day wildfire fighting before, during, and after a fire occurs. And my focus is particularly to quantify the effects of fire on the landscape and atmosphere by looking at what burns or the pre-fire fuels. My research is largely focused on the fuels that burn in a fire or the vegetation on the ground, and especially how they translate to wildfire emissions, which is one of the many aspects of fire that have a major impact on people and the environment. When it comes to our understanding of fire emissions, there is a lot of uncertainty that's caused by how we represent the vegetation that burns or the fuels, and ultimately how fuels themselves impact emissions. So we know that fuels impact fire behavior and consumption, but we want to get a better view of how that comes full circle and contributes to the quantity and composition of the smoke emissions from wildfire. And right now, fuels are contributing up to 80% of the error that we get when trying to quantify emissions from fires because we represent them in a very regional and homogeneous way that's often not really specific to the actual location of a fire. So my research seeks to address this overarching question of how to reduce uncertainty in our understanding of the composition and strength of fire emissions that result from our representation and understanding of the fuels that burn where a fire burns. To address this problem of how fuels are represented across the landscape, I use airborne and satellite remote sensing data like hyperspectral imagery and light detection and ranging, or LiDAR data, which gives specific information on the chemical and structural characteristics of vegetation to map characteristics of pre-fire fuels where a fire burns. Those fuel maps are then used to understand fire consumption and emissions through models. And as you can see, there are several types of data that I use for the machine learning models to develop fuel characteristics, maps that can be used to estimate emissions to reduce the uncertainty that we have in calculating wildfire emissions. So what I've found is that these models and the subsequent maps that I've produced are accurate. And I'm starting to work on quantifying the differences between the currently used approaches for representing fuels that are used to estimate fire emissions to using variable and locationally specific fuel maps that are produced with this methodology. And it's looking like there is a difference and a greater level of accuracy. So you can see examples of some of these maps on the right here, where each pixel represents unique vegetation characteristics. And the hope here is to continue to evaluate this methodology on different fires that have available data and continue to test the portability of this methodology. The biggest benefits of the fuel mapping methodology that I've produced is that they can be used in place of existing fuel models that are used as input to different emissions and fire consumption models, and especially allow for us to try to quantify better the amount and types of emissions from an individual fire. Also, these maps can stand alone or potentially inform management practices. And there's still so much more that we can discover and investigate here. But looking forward, the infrastructure to use this methodology is growing, which will allow it to be an increasingly accessible approach to representing fuels in the future. Thank you so much for your time.